right, and I think Mr. Peter passed out your guys' notes. So we're doing 1.4, simplifying expressions. This is where we get into combining like terms. Yesterday I put in some grades into Skyward. You guys should have seen your eCampus quiz go in, and then 1.1 practice assignment go in. I still haven't quite decided how I want to grade the practice assignment, just because prior years I normally would randomly grade it. Like some days I'll do a real quick informal check, and you guys will get your participation points for that. But this year I'm doing participation points daily, just because of what's going on. So I'm thinking that going forward, I might just pick 2 random problems from the homework and grade those. So you guys will see a 10-point grade for that. So I'm looking to put in 1.2, 1.3 by the weekend. So I'm just kind of still playing around with grades and everything for the classroom. Starting 1.4 notes. You guys do have your first quiz next week. So in module 1, it's 1.4, 1.5 notes, and that's it. And then we are going to have a quiz. It is going to be at home online, just so you guys have the same opportunity as the Seminole Connect students. All right, let's get started. Pull up my PDF. So yesterday we did evaluating expressions. We practiced our GEMDAS, all that good stuff. Today we are simplifying expressions. So go ahead and put your name on your notes. My name is Miss Lynn. We are in first period. Today is August 27th. Yeah, Christina. Notes? You don't have? Below is our standard. Key vocab, starting again with the left-hand side. Sometimes you guys in the key vocab, I just do repeats of what we have done in the prior lesson, just because it does all build on each other. This says an equivalent expression is an algebraic or numeric expression that is equal in value. For instance, 5 plus 3 and 3 plus 5 are equivalent expressions. Really quickly from last week, what property is this? Because I'm allowed to switch order. I can switch order in addition and multiplication. Begins with the C. Mia? Commutative property. Good. Then it gives equivalent expressions. Sometimes it is helpful to simplify algebraic expressions in order to find equivalent expressions. To do this, like terms can be combined using the properties of real numbers. And then again, we saw this yesterday, an expression represents a quantity. It can be evaluated but not solved. No equal sign. Okay, so we're still dealing with expressions. Like terms, I want you guys to write here, same letters raised to the same power. Same letter, or I'm going to do the S in parentheses, letter or letters, raised to the same power, or again, powers. I'm going to do the S in parentheses like that. And we're going to put examples below. A constant, a number term without a variable. I want you guys to write here a number by itself, no letters. That's your constant term, a number by itself, and no letters. Those are our variable terms. All constants are like terms. We're going to put that as well. Constants, all constants are like terms. So in other words, you can combine constant terms together. All right, let's put some examples of like terms. So I'm working down this first column here. 2x, 3x, and 10x are like terms. Why are these like terms? Lewis, what do all of these have in common? The x, right. So if I look at my definition, they have the same letter, and they're raised to the same power. Eli, what power is this x being raised to? Is there a power there? So just like the coefficient, what number do we put when we don't see something there? A 1. So really, don't write this down, but just watch here. These are all being raised to the first power. Okay, we don't say that because it's redundant. There's one x being raised to the first power. So those are like terms. Okay. Same with y squared, negative 6y squared, and 14y squared. So same idea, they're like terms because they all have the same letter, which is y, and that y is being raised to the same power, which is 2. Here, what's the coefficient of this y squared here? 1, yeah. So if you missed it, coefficient is 1, good. One more example, or 2 more, but 3a squared b, 2a squared b, and negative 5a squared b. I'm running out of room. In this case, they have the same letters, okay? So it's a squared b. Each term has an a squared b. The a is being raised to the second power, the b is being raised to the first power, but they're all the same, so those are like terms. That means we can combine them. Last but not least, you can have constant terms, so like 2, 16, negative 20. That's it, 20. 2, 16, negative 20. So if it's just constant terms, those are also like terms. You can combine them. All right, so next example, we're going to look at things that are not like terms. 2x, 3y, and 10z. These are not like terms because they each have a different letter. And the letters are different. We cannot combine them. Another example of not like terms is y squared, and y cubed. Okay? These are not like terms because they are being raised to different powers. Even though they're the same letter, they have different exponents. Another example, I want you guys to write 4ab squared negative 7a squared b and 8ab. Okay. even though these have the same two letters, the same two variables, each letter is being raised to a different power. Okay, they have to look exactly alike to be like terms. Oh, whoops. Oh no, you guys, it's AB squared, A squared B. Last example, 3x squared 4x. Okay, so just some non-examples here. All right, those things are not like terms. Okay. All right, so going back over properties of real numbers, like we did last week, I think. Associative property is the grouping of numbers can change without the sum or the product. So associative property, I'm actually going to put parentheses around this. You guys should always be thinking parentheses. When your parentheses move, that's associative property. So again, just putting some examples to this, hopefully is a review. Associative property of addition, the quantity 2 plus 3 and quantity plus 4 is equivalent to 2 plus the quantity 3 plus 4. Okay. Associative property of multiplication, the quantity of 6 times 2 and quantity times 5 is the same or equivalent to 6 times the quantity 2 times 5. Okay, that's where we can move parentheses without changing the value. So we have equivalent expressions. Okay. Commutative property. The order of numbers can change without changing the sum or the product. So commutative property of addition, I can do 2 plus 3 plus 4 is equivalent to 3 plus 2 plus 4. Right? If I switched the order here and here, that does not change the value of the expression. Same with multiplication. 6 times 2 times 5 is equivalent to 6 times 5 times 2. Okay, changing the order now in the last piece does not change the value of the expression. Last one, distributive property. We're just going to put an example here. And again, we're really going to break this down, I think, next week, or the week after, I think next week. So 4 times the quantity, let's do 2 plus 3, is equivalent to distributive property, just in the word distribute, means I can distribute this 4 through the parentheses. 4 next to a parenthesis means multiplication. So when I distribute, I am multiplying this number to each number in the parentheses. So 4 times 2 is 8. And then I have my addition sign, plus 4 times 3 is 12. Okay. Now, just to prove that these are equivalent expressions, let's solve this by order of operations. So let's just keep solving here to the left-hand side, parentheses first. 2 plus 3 is 5. Right, I didn't change anything there. And if I add these two things together, 8 plus 12 is 20. And then last but not least, 4 times 5 is 20. So we are getting here that 20 does in fact equal 20. So distributive property gives equivalent expressions. Why we use distributive property is when we have variables, or I guess I should say we have to use distributive property when we have variables. So for example, if I have 2 times the quantity x plus 3, I cannot solve this by combining x and 3 in the parentheses, right? These aren't like terms. So this forces me to distribute the 2, giving me an equivalent expression of 2x plus 6. 2 times x is 2x, 2 times 3 is 6. Okay. Just real quick raise of hands, how many of you guys are comfortable with distributive property? Like are really good at it. Okay. If you guys have highlighters on the back, it might help you to take them out if you have a couple different colors, if you would like to. That sometimes that just helps when we do like term things where we can color code the like terms, if that helps you learn. If you don't, you can square or underline. Yeah, you guys will all be putting different shapes around it too. Oops, you can just leave it there. That's fine. Okay, so just combining like terms, starting simple. When we combine like terms, what you're performing is the properties on the coefficients. So by that I mean, first of all, you have to identify if they are like terms, which 8x and 3x are. They have the same variable being raised to the same power. Since these two are like terms, I can combine them or add them together. When I add them, I'm adding their coefficients. So I'm saying 8 plus 3 is 11, and then I still have my x. How many of you understood that part? Show me. How many are like so with it? Okay. Letter B, 17y minus 4x. Are these two things like terms? No, because I have a y here, I'm going to do in blue, I have an x here. That means I cannot combine. This is the most simplified expression. Cannot combine unlike terms. So this is the most simplified this expression gets. Letter C. M and M are like terms. I can combine these two things. Okay. It's saying 13m minus, really the coefficient here is 1, minus 1m. So I'm subtracting the coefficients. 13 minus 1 is 12, and my variable is m. Letter D. I have 3 terms, only 2 of them are like terms. 3n and negative 5n are like terms. 4 is not like with the other two, okay? So I can combine my terms in yellow. I'm actually going to rewrite this. Due to the commutative property, I can rewrite, I can change order. So if I wrote 3n next to the negative 5n, and I did the plus 4 at the bottom, I can combine 3 minus 5, getting me negative 2n plus 4. So you're combining the coefficients. And then remember, this negative goes with the 5. So it's 3 minus 5. The positive goes with the 4. That's tricky. Okay. All right, so the next example, they get a little bit harder. Example 2a. I'm going to do yellow. I'll do yellow in a circle. So if you guys don't have colors, just do a circle for my like terms. 3x and positive 2x are like terms. Positive, I'm going to box the other two. Positive 5y squared and positive 4y squared are also like terms. So I'm only combining the things that are alike. 3 plus 2 is 5x. And then positive 5 plus 4 is positive 9y squared. I'm going to just go ahead and do letter C since it's already on my board here. Okay. 6n cubed. I'm starting here. What I would do is I would start with one term and then go across my expression and see if I have any others that are just like an n cubed. This one's not, it's an n squared. This last one is, it's a negative 4n cubed. Okay. And then what do I have left? I have a positive 3n squared. So I can combine my two things in yellow. 6 minus 4 is positive 2n cubed. And then I'm still writing this positive 3n squared. It's not going anywhere. It's just not combining with anything. You guys go ahead and try letters B and D on your own. Take a couple moments. Do B and D on your own. All right, you guys, letter B. Anybody want to share their answer for letter B? Natalie, what did you get for B?
2x plus 9y squared.
Good. 2x plus 9y squared. So 7x and negative 5x are like terms. Yes, Cynthia? So you added 7 and 5. We're subtracting. Remember that negative and positive signs goes with the number to the right of it. So it's 7 minus. And then positive 18y squared, negative 9y squared are like terms. Eli, what'd you get for letter D?
Negative 1 plus 6n squared plus 5n.
Good. Now, if you guys heard him or not, but he said negative 1 plus 6m squared plus 5m. So the only things that are like terms in letter D are 3 and negative 4. 6m squared is its own term here. Same with positive 5m. So Eli just brought them down with the problem. He only combined the 3 and the negative 4. Okay. Good? All right, next one gets a little bit harder with the distributive property added onto it. Do these ones together. So we want to start with distributing the 3 here in example A. Whenever you guys have parentheses, always start with simplifying them. Okay? So 3 times 2 is 6m. 3 times n is positive 3n. Then I'm just writing what I have that's left over. Plus 5n minus 4m. So now that I have gotten rid of my parentheses, okay, I'm going to go ahead and identify my like terms. 6m is a like term. Negative 4m is a like term. Positive 3n and positive 5n are like terms. So 6 minus 4 is 2m. 3 plus 5 is 8n. And again, I'm going to do C next just so I keep the same board here. All right, letter C. Am I distributing the positive 2 or am I distributing it with the negative sign? Eli? Negative 2. You always have to take the sign. I'm going to multiply through a negative 2. This 4x just hangs out outside. Okay, that's not going anywhere. Negative 2 times 3 is negative 6x. Negative 2 times 1 is negative 2. And this minus 2 hangs out at the end. So now we're identifying our like terms after I have gotten rid of the parentheses. 4x, negative 6x are like terms. And then negative 2 and negative 2 are like terms. So I'm adding my coefficients. 4 minus 6 is negative 2x. Negative 2 minus 2 is negative 4. 2 more here. Letter B, I'm distributing a -1. Okay, if there's not a number, put a 1 there. I'm distributing a -1 to each term in the parentheses. -1 times 6 is -6a. -1 times -5 is +5. And then I have this 3a hanging out at the end. Identifying my like terms. I have a -6a, a +3a, and then a +5 in the middle. Combining my a's, -6 plus 3 is -3a, and then I have that +5. Guys, make sure you keep your flow all the way down the same. Don't tack that 4y squared on all the way at the back. Keep it in order as you go down and start distributing. All right, so here you guys, I'm distributing a -1 to the numbers in my parentheses. What Ms. DePietro was saying, before I distribute this -1, you're writing the 4y squared for it first. This number isn't going anywhere, okay? So just automatically bring it down. You should write that first. Again, it flows in order of the expression. Then I do -1 times 3, which is -3y. -1 times, again, +3 again is -3y squared. And then I have a +y at the end. I'm going to keep that at the end. Okay. Identifying my like terms. I have a 4y squared and a -3y squared. I have a -3y and a +1y. So 4 minus 3 is +1y squared. -3, again, that's really +1. -3 plus 1y is -2y. One more and then we'll wrap up for the day. All right, last one, we have a word problem. It's good here. Another minute. Example 4 says, Mark burns calories at a rate of 12 calories per minute when running and 5 calories per minute when walking. Okay, so 12 calories when he runs. So he's burning more calories when he runs than when he walks. That makes sense. Suppose he exercises for 60 minutes by running. That's a long time to run. For R minutes and walking for the remaining time. The expression is given here. 12R plus 5 times the quantity 60 minus R. It represents the calories burned during Mark's 60 minutes of exercising. Okay. What does 12R represent? Take a moment, think about it. Haley, what does 12R represent? What's that? The calories he burned when he's doing what? Walking or running? Running, yep. so it's 12 calories per minute when running. So I'm going to write 12 calories gets per minute while running. They even did the variable R for running. Letter B, what does 60 minus R represent? Take a moment, read through the problem. Ben, where does the number 60 come from? 60 minutes. Good. What are they subtracting from it? What does R mean? What does the variable R mean? You have running and walking. R is. So if you're 60 minutes and you're subtracting the time that you're running, what's left over? The time that you're doing what? You subtract. Okay, let's say I went for a jog. I ran for 40 minutes. How many minutes did I walk for in an hour? 20. So when you subtracted the 60 minus R, we calculated the time that I was walking. This is the time that he's walking. Does that make sense? So 60 minutes minus the time that he's running, you get the time that he's walking. Letter C says simplify the expression. So we need to start with distributing through the 5. Distributing my 5 here. Again, this 12R isn't going anywhere. I'm just writing that down. Plus 5 times 60 is 300. 5 times negative R is negative 5R. Now I'm combining like terms. My R's are like terms. My 300. Is it? Yeah, 300. 12 minus 5 is 7R plus 300. Right, 12 minus 5, I get 7, and then that 300 just goes at the end. Guys, remember with the word expression, there is no equal sign. Last one, letter D, evaluate. So this goes back to yesterday's lesson. Mark's expression for calories burned if he runs for 20 minutes. Okay, so we are plugging in 20 to R. This means R is now equaling 20. So into my expression, it's not an equation, no equal sign. I'm plugging in 20 wherever I see R. So I get 12 times 20 plus 5 times the quantity 60 minus 20. I'm going to pause here. Are you guys okay with what I just did? I see R here in my expression. I'm plugging in R there. There's an R here. I'm plugging in 20. Plugging in 20 for R. And all I have to do is simplify using my order of operations. Order of operations, parentheses first. I'm going to go ahead and multiply. This is its own term here. I can multiply that. What's 12 times 2? 24. So 240 plus 5 times, inside my parentheses, 60 minus 20 is 40. Then multiplication first. So 240 plus 5 times 4 is 200. 240 plus 200 is 440. What does this number mean? Evaluate Mark's expression for calories burned. Calories burned. Also, you guys, word problems, get used to labeling your answer. So word problems, when you find a number, it means something. So he burned 440 calories in 20 minutes. That's what that means. Just gonna write that down. In 20 minutes. That's what we solved for.